In this problem, we are going to create our own factorial function. Now, MATLAB does have a built-in factorial function called Factorial that we could use, but we're going to investigate one way in which we can create our own. And the factorial function comes up a lot when we are looking at probability and combinatorics, so it is going to be used somewhat frequently. It came up when we did the problem with the golden ratio and in several other types of problems. So it's worth looking at how it works, and it's going to be a good exercise in using loops and planning out our problem with a flowchart first. So before we get into working through the flowchart and then eventually going into the code, let's think about how the factorial function works, and if we were to do it by hand, how we would do the calculation for the factorial. When we're starting out and for, I'll say, simpler types of problems, it's sometimes worth thinking about how would we do this manually, and then we can turn that into an algorithm that MATLAB or whatever programming language can do automatically for us. Now, bigger problems, we don't necessarily want to think about how we would do it manually, or there's a way the computer or the program could do it much more efficiently than how we would do it manually. But in thinking about the algorithm we would use ourselves, we can get at least some version running in our program. So if we look at the factorial function, let's see how we would do it by hand. Let's start with something kind of small that we could do by hand pretty easily. Let's look at how would we do 5 factorial. So by definition, the factorial, when we give it an integer, it's going to be the product of that integer and then every integer one below it, one below it, one below it until we have 1. So for example, here we are going to have 5 factorial is going to be 5 times 1 lower is 4 times 1 lower is 3 times 1 lower is 2 times 1 lower is 1, and we're going to stop at 1. Now, what we have here is 5 times 4 times 3 times 2 times 1. We can also write that as, because we can do the multiplication here in any order, that's the same as 1 times 2 times 3 times 4 times 5. So we can go descending or ascending. And the reason I wrote it ascending here on the right is because I think to program it this way, it's going to be a little bit more obvious how we do it, but just note that that order of multiplication is not going to matter. So 5 factorial is 1 times 2 times 3 times 4 times 5. So how would we do this by hand? Well, what we're going to probably do is say, well, we start with 1, and then we're going to take that 1 and we're going to multiply it by 2. So 1 times 2, and we're going to get 2. And probably when we're doing it by hand, we're going to take that result and say, we're going to take that and multiply it by 3, and we get 6. Now we can take it by 4, and we're going to get 24. 24 times 5, and we're going to get 120, and then we're done. And 5 factorial is 120. So the computer can do this much faster, but in thinking about how to program this up, what we can do, if we're going to use a loop like we're going to use here, we can kind of take them 2 at a time, or in pairs, multiply them, and then go to get that result, multiply by the next number, take that result, multiply by the next number, and so on. So 1 times 2 is 2, that result times 3, that result times 4, that result times 5. We're not going to, by hand, just look at the whole product of these, in this case, 5 digits, and instantly recognize it as 120. We're going to go in steps. So this is not the only way to do it, but this method is going to work. So I just used 5 factorial here as an example, so we could think our way through how we would do it by hand. Now we can create our flowchart for our algorithm that's going to do the same type of thing. So what's the input here? We're given this scalar integer coming in. I'll just call it x for here, so I'll call it scalar integer x. And again, thinking about how we did it by hand, that's basically going to be, if I look at the right-hand side here, our stopping point. So if x is 5, then the output eventually is going to be 1 times 2 times 3 times 4 times 5. Okay, so what we can do is we're going to always start with 1 and then work our way up to 5. We could program it to go starting at, well, x and go down to 1. I like it starting at 1 and going up to, well, generically x. but either order is going to be fine. So what we can have here is I want to start at 1, so let me establish a counter here. So I'm going to say some value of k is equal to 1. And what I want to do is I'm going to update this thing called fact. So let me also, this will be my output, I'll call it fact. I'm going to start it or initialize it at 1. Right, and we'll see why that's useful in a minute. This is going to eventually be our output. So right now I'm declaring it inside, I'm going to set it equal to 1. And what I want to do is I want to multiply this 1 by then a 2, by a 3, by a 4, by a 5, etc. until I have multiplied it by then x. So I'm going to update this scalar value of fact until I am done. So let's look down here. So I'm doing this process, the same basic process repeatedly. That's going to tell me I want to use a loop. Now, once we get into the coding, we'll decide, do we want a for loop? Do we want a while loop? What's going to be better? In this case, though, for looking at our example, if we had 5 factorial, we knew that we had to repeat this process until we were multiplying it by 5 itself. So this is a case as we look forward where we know how many times we're going to have to do this repeated step. Now, so that is going to lend itself, I would say, to a for loop, but in our flowchart, we don't have to know that yet. The flowchart is just thinking about how this is working. All right, so I'm going to start with some decision of how many times should I keep repeating my steps or not. So basically, I can ask, is k equal to x? Or I should say, is it less than or equal to x? Right, so if that's true, I'm going to do one thing. If that's false, I'll do another thing. Okay, so while that's true, while my k is, that should be less than x, less than or equal to x, I wanted to do it while my k is less than or equal to x. Okay, I'm going to keep updating the value of fact. So I'm going to set k is equal to 1. We'll see in code what we actually do, how that fits into the actual loop we're going to have. I'm initializing fact to 1, and now I want to do this process here. So if it's true, I am going to take fact, and I am going to multiply it by k, is one way to do this. Right, so notice here I'm saying fact equals fact times k, so that's just a way of saying I am overwriting the value of fact with the present value times k. So when k is 1, where we're starting off, and fact is 1, the first time through here, I have 1 times 1 is 1. So that's fine. Now I need to repeat this, though, as I go through, because I now I have the 1 times 1 step. Now I need to multiply that result by 2, then that result by 3. So this is where I'm going to repeat the same procedure over and over again, but it has to update. So I have to go here. So after it has updated the value of fact, I am going to, I'll just write here, next k is a common way of saying this. K I'm going to increment by 1. So really next k is going to be, I'm incrementing it by a value of 1. And again, we're going to see that that's actually built into the loop that we're going to use, but conceptually I have to go to my next value in k. Typically, the next value is going to be 1 more than my current value, but that does not have to be the case. All right, so I've updated my value of k. Now I'm ready to check, am I done? So with my new value of k, let's actually go back up to here. This is the loop part. I'm going to go back up to this decision and say, is the value of k now less than or equal to x? And if it is, I'm going to repeat this same left branch, the same true branch. And if it's not true, well, then I'm done. I'll get to that in a minute. So let's get back to our example here, the 5 factorial. So we go through, x is 5, k is 1, fact is 1. So k is 1. Is that less than 5? Yes. So fact of 1 is updated to 1 times 1. Well, it's still 1, but now I do next k, so k is now 2. All right, we go back up to our decision here. K is 2. Is 2 less than or equal to, let's say, 5? Yes. So we'll go back to this true branch. Now I'm updating the value of fact. Fact is 1 times k is 2. So fact is now updated to 2. And I go to the next k. K is right now 2. It's now going to be 3. And let's go back up to here. Is 3 less than or equal to 5? Yes. Let's go back down to here. So fact is being updated. Fact is 2 times 3. So fact is now 6. K is 3. It's next k. So k is now 4. And we go back up to our decision. Is 4 less than or equal to 5? Yes. So we're going to update this again. Fact is going to be updated. Is currently 6 times k is 4 is 24. Fact is now 24. Next k is now 5. Is 5 less than or equal to 5? Yes, it is. It's equal to, but that's okay. So true. Fact will get updated. It is 24 times 5 is 120 now. Now I go to next k. K is now 6. So I come back up here. Now I'm at my decision. Is 6 less than or equal to x? No, it is not. It is false. But I'm now done. I have figured out the factorial of, I'm just using 5 here as my example. That's it. I am ready to submit my answer of fact. It is now its full amount. I can return it. My function has completed its job. So this is one way of representing as a flowchart or as the algorithm what we are doing when we were on the right-hand side, at least. It's 1 times 2 times 3 times 4 times 5, or for whatever integer value of x we give it, it's going to do the correct procedure. So if I say I want 10 factorial, well, then this algorithm should also work for that. It's just going to repeat this branch, this true branch, more times until it's figured out 10 factorial. And then when it's done with the loop, it's going to return back or report back the value of, well, the factorial of 10 or 10 factorial. So this looks good, and our function only has to handle integer values, positive integers, but actually there's one more piece of this that we should be able to handle. Even though it does say given a positive integer, scalar integer, let's worry about one special case here. So 1 factorial is just going to be 1. So that's fine. Let's make sure it can handle 1. So if x is 1, k is 1, fact is 1. Is 1 less than or equal to 1? Yes. Fact is 1 times 1 is 1. And that's good. But there is another case that comes up quite a bit, and that's 0 factorial. Now, technically, from the rules that are given in this problem, we don't have to be able to handle 0. The function only has to handle a positive integer scalar. Let me actually change that to non-negative. So we do want to be able to handle 0 because it comes up. 0 factorial is actually 1, though. If we look at our algorithm right now, or our flowchart, if x is 0, k is 1, fact is 1, so that's fine. Now we have here, is k less than or equal to x? So we have 1 is less than or equal to 0, that's false. So actually this way that we wrote our algorithm is okay. It will be able to handle an input of 0 correctly because it just won't even go into the loop. It's going to go right into false and report back fact. But because we initialized fact as 1, it actually does deliver us the correct answer for 0 factorial. So this kind of edge case, this weird case, it turns out the way that we set up the algorithm does work correctly for 0 factorial or 1 factorial or any positive. It should work for any positive integer that we give it. But so it turns out it does work, so that's nice. So now let's take this algorithm and actually think about how to implement it in code. But before I get there, let's look at kind of things I'm going to group together here into the loop. Now, I already said we know up front, or we'll see that we know up front, how many times to repeat this loop, because we repeat it, well, basically the number of times equal to whatever x is. So we know up front how many times to repeat it, so I'm going to say that this lends itself to a for loop. We could use a while loop. Basically, anytime we can use a for loop, we could instead use a while loop. Vice versa is not quite true, but if we can use a for loop, we probably should use a for loop there. I think they're easier to keep track of. It's harder to go into an infinite loop. So let me just mark here the things that are going to be involved in the loop, and that's going to be kind of these standard things that involve our counter. I just called it K. But basically this piece here, this decision is going to be part of our loop. If we see here, this arrow always, that indicates it's a loop. The next K, that's going to be part of the loop. The for loop automatically is going to increment our value of K. Now, if it was a while loop, we would have to manually do this, so we would want to think about that. And the initialization of K, actually that also will be handled by the for loop. Again, if it was a while loop, we would probably have to initialize the counter ourselves. We would have to set up more carefully this decision here, and we would have to set up our incrementer a little bit more manually if this were a while loop. But a for loop, a nice feature of it is these things are kind of all going to be baked into it. So yeah, I've marked that with this green dot here because this will be kind of integrated right into how we set up the for loop, and we can think about it that way. The things without the green we'll have to think about separately. All right, so we have the basic structure of our algorithm. Now let's go into the code and actually implement this, and then we want to test it too, because we can test it against Factorial, which is a built-in MATLAB function. Make sure we're getting the right values, because we should get at least the same output as Factorial gives us, even though we are going to be doing it a slightly different way than MATLAB is. Now in MATLAB, we want this to be a function, so I will have the first line be the function to define it here. In the flowchart, I already decided, I don't have to stay with it necessarily, but I already decided that I'm going to call my output fact for the factorial of my input. And that's going to equal the name of my function. So for the purposes of this demonstration, I'm calling it compsci200 L03 facto. So we see it matches the name I already gave the M file. And we're going to take an input, well, again, in the algorithm or in the flowchart, I called it X. I will just stick with that. All right, and putting the skeleton together, I'll end that with a return or an end. Let's just change it up. I'll do it with end. Actually, end seems to be a little bit more accepted in MATLAB now, so I will use end or return interchangeably when I'm defining a function. They're both going to do the same thing. In this case, I will finish it with this end statement. All right, so let's look at the algorithm. We're starting with a scalar input x, which that's coming in, so there's nothing more to code. That's really how we defined the function. Then we're going to get to this k equals 1, which I'll write it down for now, but we're going to see we actually don't need to code it, so I'm going to comment it right out, but I want to kind of follow the flow of my flowchart for the moment. All right, fact equals 1. All right, so I'm initializing the value of my output to 1, because in this case, I'm going to be updating its value in my loop. I'm going to keep overwriting its value. This is different than other times where I want to have a vector of values and I want to add another element to my vector as I go. This one, I have a scalar. I just will keep overwriting it until I have the answer I want. Now we're at this decision. And again, I marked this as being part of the loop. I know that I want to use a loop for this. And because I know how many times this has to run, I know I want to make this a for loop. So the for loop is going to initialize our counter. It's going to increment our counter. All of that will be baked into here. In the flowchart stage, we don't have to know that. It's when we implement it in the code that we do. So I'm going to choose an index variable called k. That's what I did in the flowchart, so I'll just stick with that here. And I'm going to say that k is going to start at a value of 1. It's going to increase by a value of 1 because we're doing 1 times 2 times 3 times 4, so its value should go up by 1 every time until it is equal to x. Now in the for loop, in the statement here, 1 colon 1 colon x, this is initializing its value to 1, so that's already taken care of. I don't need this line of code. It's incrementing it by 1. That's the next. And it's saying keep repeating the stuff inside here until it's no longer true that k is less than or equal to x. So for a for loop, it's always built in here that whatever this value is here at the end, it's going to stop when this variable is not less than or equal to this variable. So keep in mind, it's a less than or equal to, not strictly less than. So it will run when it's equal to the value here. And that's what we want here. We do want it to run when k is 5, or k is x in general, because that'll be the last time it needs to run. All right, so this for loop is already accounting for now kind of all the things with the green dot. It's making the decision for us. It's incrementing it for us. It's looping it for us. I have to end my for loop, which so I'll again put that kind of skeleton together. So that's going to be the loop part. Incrementing, initializing, and testing it for us. So actually all the green dots are in line 7 and line 11 right now. So now, while this is true, when I'm inside the loop, so that's the true branch of this consideration, I need to now do the processes inside, or the statements inside. So fact equals fact times k. And then the next k, again, that's baked right into the for loop. So actually this is all that has to be done inside the for loop. So what's going to happen, it's going to keep doing this statement while it's true. It's going to keep overwriting the value of fact with fact times k until I get to a k value bigger than x, in which case I'll go to line, 12 or whatever is after my loop. And if we look at our flowchart, our algorithm, once we're kicked out of the loop, it's going to go and return fact. And that's what line 16 is doing, is returning fact, because that's what I defined as my one output here. So an end or a return is that output block in our algorithm. So actually, believe it or not, this is all the factorial function has, or it's one way to implement it. So let's save it and test it out. So let's say x is 5. Let's check out our function. Make sure it works. And pressing evaluate here, we get 120. And that's what we should get. Let's test the built-in MATLAB function, factorial of x. And it gives us 120. Well, we already did this one by hand, so that's good. Let's do a different one. Let's just say x is, 10 I talked about. And let's see how our code does. All right, so this we didn't do by hand, and already it's getting pretty big here. So that's a bigger answer than we tried to do by hand. But let's try the built-in factorial, make sure we get the same value, and we do. Now, let's try something even bigger here that we definitely don't want to do by hand. There's going to be certainly a limit as to how big a value we can use here. Let me try 40. So it rounds off quite a bit, or it puts in scientific notation. Let's see what we get when we do it with the MATLAB version, and we get the same number. Now, if we try to do this on a calculator, there's probably, usually on like calculators, 70 is the limit that it's able to do. Let's see if ours can go bigger. All right, we can do 70 in here. We see we have an e to the 100, or times 10 to the 100 power. And the MATLAB version, same answer. So not very interesting here, but we can put in big numbers, and it seems to be getting it correct. Let's try those edge cases, though. Make sure it's doing it correctly. When x was 1 is the first example. We get 1. 1 factorial is 1. Yes, so it does that correctly. And finally, let's try that other case of 0 and put it into our algorithm. And we get 1 back. 0 factorial is 1, and that is true. And that's coming from the fact that I am doing this initialization here. So even when x is 0, it actually never goes into this loop at all, but it still spits out a value of fact of 1, and that is correct. And if we just double check that with what the built-in one does, we get 1. So for non-negative integers, 0 through whatever we want, our algorithm, our function, is returning the right value for the factorial.